guess we can get started. So, hi, this is MM Mondays. For anyone who hasn't been on one of these before, my name is Ryan, and I basically go over a bunch of different ML topics in a relatively quick way for people to get introduced to the topic. This is going to be our last one, at least for this semester, and we're going to be talking about something known as stable diffusion. So, I guess just to clarify things, this will be recorded. The slides will be available on the Discord afterwards. And in case, for some reason, like if you need to go back and check something, if you want to get an idea of how something works again and spend it like a month or so later, you can always go back. But I guess for today, we're going to talk about stable diffusion. So I'm basically going to, unlike some of my other weeks, we're going to be going over kind of building up to what stable diffusion is based on some simpler concepts. And I'll kind of direct you guys to how you can end up using stable diffusion. So I guess let's start with something simpler. What's a diffusion model? Instead of being specific to stable diffusion. So they're part of a group of models called generative models. As is kind of alluded to by the name, they generate data, generate like a larger quantity of data based on something they get. So if you are generating a picture, that's a generative model. And the reason it's called a diffusion model is because the process is kind of similar to how diffusion works in real life. Specifically, how these work is you add noise. So basically, you can see as you go from left to right, there's more and more noise added via like a random process. And the goal, weirdly enough, is we can reverse this process, going from really noisy to something that actually looks pretty nice. And I guess kind of the goal of the model itself is to learn the nature of natural images, because an image that's been taken a picture of real life, there are like a lot of patterns intrinsically that make it easier to represent. Before I go any further, just as a reminder, if anyone has any questions, comments, or concerns, please, you can kind of go right ahead and say them, to be honest, and I'll do my best to answer them, because the whole point is to learn. But moving on. So in a diffusion model, there's two things. The simpler one is forward diffusion. So in forward diffusion, basically we just add noise to a model until we can't tell what it was a picture of initially. So in this case, it's a picture of a dog. Basically just add noise, noise, noise. Eventually you get to a point where it's not like necessarily clear specifically where you can't tell, but there is a point where you can no longer tell it is what it was. So think of it kind of, I have the analogy on here, kind of how real life diffusion works. If you were to put a drop of ink in water, after enough time, you won't be able to tell where that drop was put. But earlier and earlier in the process, you would be able to tell, you have a better and better idea as to where that drop came from. This is kind of a similar process. Now, the $1 million question here is, how do we reverse this? Because if we can do that, we can make some really cool things out of what's effectively noise. But that is not exactly, that's kind of a not trivial question, right? This is just kind of random. But there is a way. I guess, first of all, does anyone have any, I'm kind of curious what kind of thoughts you guys have concerning how could we do reverse diffusion? Does anyone have any thoughts? If you don't, that's all right. I'm just curious. I just want to see if you guys have any. It's not exactly an easy question. I'm just curious what you guys are coming up with. But if not, I can move forward. Basically a way of doing this, there's a there's a model known as a noise predictor. Basically what they do is they take an image and they predict how much noise was added to the image. So over here, as a human, you can tell this has no noise in it. This is like a pretty much clear picture of something. As you go further and further, there's less and less noise. But being able to tell how much noise is added is crucial for figuring out, basically, it can kind of be used to guesstimate how much noise, how like to change an image to become something that makes more, that like is more realistic. So with those, we actually have a way of doing reverse diffusion. So basically, we start with a random image. It's just noise, it's random noise. We predict the noise from that image, subtract that noise, predicted noise, and we just keep doing that a bunch of times. And eventually you'll hit something that is a pretty natural looking image from what's effectively nothing. It's not gonna necessarily look like this, like just because I fed in that, if I'm training off of this image, that doesn't mean it's going to produce that image. It's a little bit more complicated than that. But the idea is the image itself has like natural qualities, it has patterns that make sense, it's not pure chaos. And that's the idea. Does anyone have any questions about how this process works? Okay, then there are some issues with this that might not be inherently obvious, but this is really slow. Doing this is really slow. If you were to try to like do this on like anything less than a really nice GPU, it's going to take a really long time, and even if you do have a nice GPU, it'll take a bit. Just because you're dealing with a large image and doing a lot with that image. So for instance, a 512 by 512 RGB image is going to have an input. It's going to have a lot of different values, basically a huge number of possible. So imagine it like a vector. If you were to like compress it into like just a smaller line of values, it would be over 700,000 dimensions. It'd be a crazy amount to deal with. It's just a lot, and we need to find a way to like kind of deal with the speed issue. Otherwise, it's just kind of unusable. So there's a way we can deal with that, and that is something known as latent diffusion. So basically, this all comes down to the idea that if you were to basically take an image and compress it and put it into a form where it retains all of its information, or at least all the meaningful information in the smallest space as possible. Because natural images and stuff like that tend to follow certain patterns. It isn't pure randomness. So you can actually compress images a fair bit using this process. It's called the latent space. It's about 48 times smaller than the pixel space. So it is a lot smaller, and because of that, it can be worked with a lot more quickly. To actually convert these things, there's a certain model that exists already. It's called a variational autoencoder. That the actual implementation of that isn't super important. It's basically just a model that learns how to represent like pixel images into latent images, and latent images back to pixel images. It's basically learning how to represent an image in a smaller fashion. It's like learning how to compress something, basically. But with latent diffusion, we can actually get to the topic of this discussion, stable diffusion. So if you've never heard of stable diffusion before, it's only come out in the last year or two. It's pretty new. But basically, these are a type of model that they use diffusion, as you might guess from the name, and they use latent diffusion to generate high quality images from a text prompt. So if you were to use that QR code, that's a link to a API where basically it can do it a lot more quickly than your own personal computer, but it can take in text and give out this kind of image. So this is actually one of the results I got when I put in a high text solar farm utopia in the Amazon rainforest, and I got a pretty nice results. But there's something I kind of skipped here, and there's text. I haven't mentioned text at all up until now. How do you get text into this whole process? What do you do? It's just kind of, so far all we've been dealing with is basically taking static and making whatever image out of it. How do we adjust that? The process of actually handling that is something known as conditioning. The term's not super important, but basically it's the idea where you can take in, there's models that exist out there. There's natural language processing models, which can take in text and basically convert them into a certain simpler form, kind of like what I mentioned before in terms of converting from pixel space to latent space, compressing important information to a smaller piece. You can basically take that. You can take text, convert it into a pretty small form, and then feed that into a noise predictor, and it'll bias it toward like cleaning noise in such a way where it creates images that kind of follow from the text. So the whole process, this is just an example, I give how that works, but first of all, we make a random tensor in latent space. In other words, it's basically just making a random image, just pure noise. And you want to take that noise and have a noise predictor kind of predict how much noise there is, or like not necessarily how, but where the noise is. And it also takes in a text prompt. And using both its training and both its training in terms of general diffusion as well as the text prompt, it can predict noise in such a way that it biases toward the image indicated by the text. So you remove the latent noise, repeat it a few times, many times, it takes more than a few times. And then once you do that, you use so this is like the variational autoencoder I mentioned before. It's all being done in latent space, so it can actually be done reasonably quickly. We'll just be using that encoder to convert from here to an image that we can actually see and appreciate. So again, this representation over here in this picture is a little bit misleading because it's doing the whole thing in pixel space, so it's easier to see. But the idea still stands. If you don't do it in what's known as latent space, it just takes a really long time. This is much faster, and you can actually do this. Even if you're using even if you did see the QR code I put in earlier, even that takes like a bit, depending on how much time there is. But that's because they're using huge computers and they're using huge cloud setups. And even then, it still takes some time, and that's only because the only reason it's taking a short time is because it's doing these speed ups. So, does anyone have any questions about any of this? I understand I'm going kind of quickly. I just want to see. I kind of want to see what you guys have questions on, because I'm not sure. I can't assume that you guys know any of this, which is why I'm trying to ask. So I'm going to go back to the full process right here. So in terms of actually using Stable Diffusion, there are some nice ways. I showed you a link before to an API where you can do this. There are also a number of ways where you can basically download the source code and work with it directly and do things like that. And there's also a software called Easy Diffusion. I am going to warn you, a lot of these things are really RAM heavy. It takes a lot of RAM to run them. I think even with the Google Collaborative CPU, I ran it earlier today, and it actually won't. Let me just escape here. It actually, if you were to run this, it actually would hit the RAM limit before you actually finish generating the image. If you have Google Colab Pro, then you're fine, but I don't know how many people here actually use Google Colab Pro. I don't. So another option is to use a kind of a implementation known as Easy Diffusion. Again, I have a link to this in the slides, but basically, this is like a setup that someone made that allows you to kind of get into Stable Diffusion more easily. It has some things in it that allow you to, it will take longer if you don't have a good GPU. It can still be done with a CPU, but it's a lot slower. Let me see how it, let me just show you how this, let's see, where's it good? But you can get stuff like this. So it will sample a bunch of images after a bunch of different iterations. Because it's based on noise, you're going to get a lot of different images that are kind of going after the same thing, which is nice for what we're trying to do. You get a lot of different images that, it's a matter of creative choice as to what you go with. But it is a pretty good way of approaching it if you don't want to pay money for Google Cloud Pro. So it's a bit of a pain because this is a relatively new technology that is pretty computationally intense. So it's a little hard to just make. There's a reason I don't have a workshop for this particular one. It's just kind of, it's too new and the setup's too. It's just kind of hard to work with. I have these setups where you can kind of play with it more in your own time, depending on your own computational, like whatever you have the ability to actually do. But does anyone have any comments, questions, or concerns about anything I've gone over? Why you might want to use Stable Diffusion on something? I guess, etc. The floor is open. I believe so. Dolly used a similar process. They didn't actually use the latent space, which is interesting. So Dolly's like arguably an earlier version of this, which is why I thought this is a pretty new thing. The idea is pretty similar, but it's slower. So Stable Diffusion can do it more quickly. That's also part of why there's also like different quirks in the implementation, which for this allow you to get much cleaner images than Dolly would. Like a lot of these images are pretty much photorealistic or close to it, as opposed to Dolly, which sometimes has some issues comparatively. Any other comments, or questions or anything? I know we have a lot of time left. There's only so much I can really go over on this, so I'm asking if anyone has areas they want to specifically look into when it comes to Stable Diffusion. All right, so I guess I will end a bit early. If anyone has any questions or things they want to talk about after the recording, you can do so in a minute. But yeah, hope you enjoyed, and